Hello students, good time to all. I am Chandan from Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss energy transport and intensity of wave in case of plane progressive wave. Let's begin. When a plane progressive wave propagates in a medium, throughout that of medium, the particles are successively set into vibration due to elasticity of that of given medium. In this way, energy is transferred from one particle to other throughout that of medium when that wave propagates. So, we consider a plane progressive wave. The equation of that wave, generally we know y is equal to a sin omega t minus kx. We are familiar with all these terms. Y, the instantaneous displacement of that particle at distance x, a is the amplitude, omega angular frequency, k propagation vector, propagation constant or wave number. Now, differentiating that equation with respect to t, differentiating above equation with respect to t, we get del y del t is equal to del by del t a sin omega t minus kx or del y by del t a del by del t of sin omega t minus kx or del y by del t is equal to a, its differentiation cos omega t minus kx, inside that of bracket term differentiating we get omega. So, omega cos omega t minus kx, and equation number 2. Again differentiating with respect to t, again differentiating with respect to t, we get it is del square y del t square is equal to del by del t of that term a omega cos omega t minus kx or del square y del t square is equal to minus a omega square sin omega t minus kx or del square y by del t square is equal to minus omega square a sin omega t minus kx, that is the y, minus omega square y, that equation number 3. These two results are important, del y by del t and del square y by del t square for upcoming calculations. Now, we consider a cylindrical region. Let we consider a cylindrical region of that medium of unit cross sectional area. Look here, if that is a plane progressive wave, that is a transverse plane progressive wave, the particles are vibrating throughout that of medium in SHM. If we take a cylindrical region here, a cylindrical region, and that cylindrical region where that cross section, here the cross section is unit cross section, and the thickness, here the thickness be dx, dx is the thickness of that of cylinder which is at a distance x from the source. If that is the source, then that dx from the distance x to that of source. So, we consider a cylindrical region of that medium having unit cross section, that cross section is unit cross sectional area. Here we consider a small thickness dx of the cylinder at a distance x from the source, that is the source. Now, the volume of this layer of cylinder, volume of the layer of cylinder that is area into thickness, area into thickness. Let the volume of that layer of cylinder, small volume dV, here the area is the unity, that is 1, thickness is the dx. So, dV is equal to dx, the volume of layer of that cylinder. Let the density of the medium, let the density of medium is equal to rho. Therefore, the mass of the layer of medium, therefore, the mass of layer of medium is m is equal to, that is density into volume, density into volume, density rho, volume dV, or mass layer of the medium m is equal to rho, dV is equal to dx, rho dx, as dV is equal to dx. Now, the total energy of that of layer is due to its kinetic energy plus potential energy. First we calculate the kinetic energy of the layer. Therefore, the kinetic energy of the layer, that is T is equal to half mv square, mass velocity of that of layer, or T is equal to half mass, velocity, rate of change of displacement, del y by del t whole square. Here we get the value of del y by del t. Now that value is put here, or t is equal to half, in place of m we substitute rho dx, in place of del y by del t it is a omega cos omega t minus kx square minus kx whole square, or t is equal to half rho dx a square omega square cos square omega t minus kx kinetic energy. Let equation number 4. Then we calculate the potential energy of that layer medium. To calculating the potential energy, first we calculate what will be the force acting on that of layer. The force acting on that of layer, force acting on the layer, F is equal to mass into acceleration, mass into acceleration. F is equal to, here mass m, acceleration second order differentiation, del square by del t square. The values of m and del square by del t square is put here. So F is equal to the value of m, rho dx, second order differentiation of that of displacement, minus omega square y, which is equal to F is equal to minus omega square rho dx into y. That is the force acting on the layer. Now the potential energy of that of layer is nothing, that is the work done in displacing that layer through the distance y, that is the displacement, the distance y from its equilibrium is the stored as the potential energy of the layer. So what will be the potential energy here? Potential energy nothing, that is work done in displacing the layer through y from its equilibrium position is stored as potential energy of the layer. Therefore, the potential energy of the layer U is equal to integration from negative sign integration from 0 to y f dy, or U is equal to minus 0 to y, the value of y is put, value of f is put here, minus omega square rho dx y, minus omega square rho dx y to dy. The constant of minus minus plus, so omega square rho dx to the outside, integration from y dy is equal to omega square rho dx it is y square by 2 from 0 to y. Using upper limit and lower limit, we have omega square rho dx y square by 2, or energy U is equal to, potential energy U is equal to half omega square rho dx y square. That equation number 5. Therefore, total energy of the layer E is equal to kinetic energy plus potential energy, or E is equal to kinetic energy T plus potential energy U. The value of T and U is put here. So, the value of T that much, right? The value of T half rho dx a square omega square cos square omega t minus kx plus the value of U, and again the value of y is put here. So, half omega square rho dx, the value of y is put. So, we have a square sin square omega t minus kx, or total energy E equal to, here we take common as half rho dx a square omega square, inside that of bracket sin square omega t minus kx plus cos square omega t minus kx. Sin square theta plus cos square theta is equal to 1, that value is equal to 1. Therefore, total energy is equal to half rho dx a square omega square into 1, or is equal to half rho dx a square omega square. That is the total energy. Next, we calculate energy density. Therefore, energy density is equal to total energy per unit volume. Total energy per unit volume. Here total energy is equal to E, unit volume dV is equal to dx. So, unit volume is equal to dV. That is equal to dx. Now, the energy density is equal to E by dx, which is equal to half rho dx a square omega square divided by dx. Dx cancel out. We have half rho a square omega square. Now, omega is equal to 2 pi nu. Nu is the frequency, where nu is equal to frequency term. Therefore, half rho a square 2 pi nu square. Finally, we get 2 square, 2 cancel out, that is equal to 2 pi square nu square rho a square. That is the term of energy density. So, energy density depend upon the frequency, density of that of medium and amplitude, but that does not depend on x and t. X at particular position and time. Now we have to calculate the intensity of wave. Intensity of wave, intensity of wave, or we can say it as the energy current. Energy current, intensity of wave or energy current, which is nothing, that is the total energy of the wave passing per unit area of the cross section per second. That is the total energy of the wave passing per unit area of cross section per second, where that cross section which is perpendicular to the direction of propagation of that wave. In case of energy density, is the energy contained in a cylinder of unit length and a unit area of that cross section, and the wave travels with the velocity of v, that is v in 1 second. Therefore, the energy flowing per second for unit area of cross section will be the energy contained in that of cylinder of length v and unit area of the cross section. So, the total energy of wave passing per unit area of cross section, that can be written as the energy density into wave velocity, So, intensity of wave I is equal to energy density into wave velocity, or I is equal to energy density 2 pi square nu square rho a square wave velocity, that is v. V is the wave velocity, v square, wave velocity just v. So, intensity of wave I is equal to 2 pi square nu square a square rho v, the intensity of wave, or we can say that is the energy current, the intensity of wave or energy current, that depend upon density of that medium, wave velocity and square of amplitude of that wave and frequency of that of wave. So, with the help of this video lecture, we understand energy transport and intensity wave for plane progressive wave. We consider the equation of plane progressive wave, differentiate with respect to t, again differentiate with respect to t. These two equations are helped us for deriving. Consider a cylindrical region of that medium layer. We take volume, density of that medium, mass of that of medium, kinetic energy, then force acting on that of medium, on that of layer, and then calculating the potential energy, total energy, sum of potential energy and kinetic energy, energy density, total energy per unit volume. Here is the expression for energy density, and now the intensity of wave, or we can say that is the energy current, which is the total energy of that of wave passing per unit area of the cross section per second. So, the total energy passing through that of unit area of cross section, which is the energy density, which into the wave velocity. So, energy density into wave velocity, that is the expression for intensity of wave, or we can say that is the energy current for a plane progressive wave. So, with this useful and informative notes, let me wind up this session. Thank you.